Okay, a real image, there's really light at the image. A virtual image, light only appears to be coming from there. And the easiest way to tell the difference is, which side of an optical element does the light leave from it? The outgoing side. Agreed? So if the image is on the outgoing side, the image is where the light actually went. If the image is not on the outgoing side, then it only appears that the light came from some spot. It didn't really. Okay? So, for example, if I have light diverging from here, and it hit your eye, you would all say, oh look, there's a thing here. If, on the way to you, I bent that light like this, you would say there's a thing here. Well, it turns out there isn't. The thing was here. But your eyes interpreted the light that came to you as though it was not bending between you and the thing you focused on. But since you didn't see light that was on the outgoing side, it isn't true that the object was not messed with when you saw it. So if you see the image on the outgoing side, you're seeing the thing that's really there. Okay? And that's what makes it real. Okay, finally, the last step. Distance, object 3 is what? 0.57. And where are objects supposed to be? On the incoming side. Is this object on the incoming side?
No.
No, it's not. Remember to look at the second pass for the lens down here. This object is not on the incoming side. So this object distance is negative. Focal length 3 is?
-1, -5.
Still -5, just like always. So 1 over minus 0.57 plus 1 over distance image 3 is 1 over -5. Distance image 3 is what?
0.64.
So that's 0.64 centimeters on which side? Outgoing side, because the image distance is positive, and image distance is positive when the image is on the outgoing side. So this thing is 0.64 away from there.
I'm getting negative 0.64.
I hope not. Did you?
Probably forgot the negative sign.
I think you lost the negative sign on the 0.57 when it moved to the other side of the equation. But you're going to have to take 1 over -5 plus 1 over 0.57. 1 over 0.57 is a heck of a lot bigger than 5. What is M3?
1.5. I'm getting 1.5.
Okay, so what is M3?
-0.64. What? I got 1.1.
You know? What's the total magnification? How do I get the total magnification? What do I do? Multiply. I take M1 times M2 times M3. So I can see that M1 was positive, M2 was negative, M3 was positive. So the product of those three is going to be a negative. Minus what? 0.16. So yes, this thing is completely tiny. It is only 16% as big as the original. it's flipped. The final image, real or virtual?
Real.
Real, because it is on the outgoing side. You look at D3, D3 says that the last one is on the outgoing side, so it is a real image. Overall, right side up or upside down? Upside down. Overall, enlarged or reduced? Reduced. So that's it. So what do you think?
And it's real or virtual? Real, right?
It's real,
Yeah.
because the image of the last optical element is on the outgoing side of that optical element, making the image real.
Where does the image end up with respect to the .64?
The image is 0.64 from here.
All right, from the center, okay.
Yeah, so I need to... And it's really small. Right over there, but it is real. What do you think?
Oh.
It's okay? Yeah. Don't use the word switch in your mind, okay? Just use the following principle. Light goes through a lens and bounces off a mirror, okay? So if you just follow the light starting from the object, ignoring where all the images come, because a lot of people try to do something crazy occasionally when they get a virtual image. They try to turn the light around to make it head towards the virtual image. So you remember in this problem, the very first image was here. A lot of people are tempted to say, oh, I know what happened. The light went to the lens and it bounced off the lens. And then people say, how could the mirror ever see anything? Because wasn't the light going this way? No. Through a lens, off the mirror. So, through the lens, off the mirror, and then you got to go back through the lens because it's in your way. Yes. So, for the lens, the first time through, the light was going from left to right. For the mirror, the light was in left, out right. And then for the last pass through the lens, it was just going from right to left. Because that's the light that we're using at that point. So, what do you think? Good? You like it?
Very short for that.
All right, moving on. A particular person's nearsighted eye has a near point of 12 centimeters and a far point of 17 centimeters. Okay? You will place a lens 2 centimeters in front of their eye. Calculate all the following. Blah, 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 blah. Okay? Now, what does this business about near points and far points mean? Okay? What it means, what does the most focusing in your eye? What part of the eye? The lens does not do the most focusing in the eye. Cornea does most of the focusing. The lens does a little bit of adjustment, because if you didn't have a lens, there would be only one distance that objects could be where they'd be in focus. And that would not be to biological advantage. Oh, I got killed by so-and-so. Why? It was too close to me and I couldn't focus on it. So the lens in your eye allows for minor adjustments on the focusing of your cornea. In the best possible case, you can focus where the object is as far as Where? Nope. If your eyes need no correction, where is your far point?
Infinity.
Infinity. Okay, and then you will have some near points that will change with age. As you get older, the near point will get further and further from you until it gets longer than your arm, and then you can't read anymore, and then you need glasses. Okay? Now, if you're nearsighted, you can't see without glasses objects that are far away from you because they're beyond your far point. But fortunately, people who wear glasses don't look at objects. I don't look at you while I'm wearing my glasses. What do I look at? I look at a virtual image of you. So what my glasses do is they place the virtual image at a location that my eyes can handle. And then my eyes handle it from there. So the idea of designing these prescription lenses is to place the image from the lens at a place where the eye can handle it from there. And what we've got is that the eye can handle everything for this person between 12 and 17. Okay? Now, the definition of an eye that doesn't need correction is that the far point is infinity. So what I would like to do is take an object at infinity and place the image from that object at this person's far point. And then everything is cool, they can see. Does everybody follow that reasoning? Okay? Take the object of infinity, place it at the person's far point, and you're all done with their glasses prescription. Everybody agreed? So, I'm going to make a diagram. For this person, what are they, nearsighted or farsighted? Nearsighted. So, here's the eyeball with the cornea that does most of the focusing. The lens is behind it. The retina is back here.
Oh man, I can't see it.
And these distances tell me that 17 centimeters from the face of the eyeball is this person's far point. That is the location where I want to put the image of an object that is at infinity. Everybody follow that reasoning? Okay. And what kind of a lens am I going to use? Converging or diverging? Diverging. Diverging lens. So, to simply repeat what we said.
Why is it a diverging lens?
Because the diverging lens will put the virtual image closer to it.
Doesn't a diverging lens also increase your focal point? So nearsighted people they have short focal point.
What is, okay, the way you're phrasing it is a way you would phrase it to a customer in a store when you were selling them glasses. Okay? I don't want you to phrase it that way. In here, what I want to say is, this will allow you to see an object at infinity by placing the image of that object at 17 centimeters. So to a person, you would say, you can now see an object that is further away. So as though you've moved something about the person's eye. We don't affect the eye. All we do is we put an image where the eye can handle it. And so what it'll mean is your eye can now handle an object that was at infinity because you're no longer going to be looking at the object. You're going to be looking at instead an image of that object placed to the location where you can see it. So, this is not very much to scale because this is 2 centimeters. Okay?
Wow.
Right. Most people don't wear glasses like this. Hey, how you doing?